Hello, it's Keith here, and this is lesson 22 of the Suck Hunt series of Z80 programming tutorials. We're looking at my little Suck Hunt game again, and this time we're going to be looking at the Sega Master System. And the Sega Master System is quite different from the other systems. Now, the Sega Master System has a light gun, and the Sega Master System also has shutter glasses, and this is really the system that the game was designed for in a lot of ways. I wanted to try and take advantage of both of those functions. Now, the only problem with the Sega Master System is it can't do the XOR function that the graphics rely on, which posed quite a problem, and I've had to come up with some workarounds about it. Now, the 3D effect, unfortunately, for the anaglyph glasses can't be done properly because this required layering two layers over each other, and the Master System doesn't have two layers, it doesn't have transparent effects. So what I'm having to do is, for the 3D glasses, we're having to flip between the two images anyway, and then for the anaglyph glasses, I'm toggling between the two colours, which you can see here, it creates quite an uncomfortable effect, unfortunately, but it does work, and if you had a CRT, I'm sure it would look fairly decent. Not so good on a TFT though. Anyway, you can see the introduction of the game just flying away there, and we're going to be looking at the code today. Now, as I say, the main game on the other systems was designed for bitmap-based screens. The Master System is the only tile-based system that it supports. I really couldn't be bothered to port it to any more systems, and the reason the Master System was a priority because it has that light gun and that shutter glasses effect. So we're going to have to convert the bitmap sprites into graphics that we can load into tiles and sprites. Now, the cursors are going to be done with sprites, but everything else is going to be done with the tile map, so we're not technically using sprites for our sprites, if you see what I mean. So what I've had to do is I've had to convert all of the game graphics. You can see here are the gameplay sprites, and these have been converted automatically by Sprite Editor into a tile bank here, and these are all of the patterns that we're going to need to create our enemies. And you can see here, this has removed any redundancy, and I had to do a little bit of optimization. The clouds were a bit simplified and things to reduce the number of tiles to fit within the Master System memory, because we've got these gameplay graphics here, we've also got the font, and we've also got the cursors and things, so had to minimize things down a bit. Now, when it came to exporting the information about the game, as always in the past, I've used this export info function here, but there's an extra version called export tileset, and what this does is it will export the information on these sprites, their relative sizes, but it will also export a tile map of how to, for example, build up this graphic from the numbered tiles in this tile map here. So Sprite Editor is doing a lot of the work of helping me with the rather annoying challenge of porting this game to this system. Anyway, let's go over to the source code. Let's take a look. Okay, so the first thing I think we're going to discuss is we're going to discuss interrupts. So Suck Hunt uses interrupts in two different ways. Firstly, we're loading our interrupt handler, interrupt mode 1, memory address 0038 here. That's our interrupt handler that's going to handle the 3D effect. It has to switch between the two tile maps and the two 3D palettes if required during the interrupt. It also handles the music and also the light gun. If the fire is pressed, it handles the flashing of the screen and the detection of the light gun position. Now, I've covered both of those things in previous examples in the platform-specific series, so I'm going to go over them relatively quickly today. If you need more details, please see the light gun example in the platform-specific or the shutter glasses example in platform-specific. The other thing is, for configuring the game, I actually needed more buttons than I had available to me. We have fire for firing, fire 2 for reloading. I needed another button for pausing and for reconfiguration. So what I've done is I've used the pause button. So that's the button on the console itself. That doesn't register as part of the joypad. It actually causes a non-maskable interrupt, a jump to memory address 66. So this will happen every time the pause button is pressed. It's not a press and a release or anything. It just, every time you press that button, another NMI is caused. So what I'm doing is I'm writing a 1 to the pause button flag here, and we're going to handle that within our code for when the pause button is pressed the first time to pause or a second time to release. And it can also be used on the title screen. If I press it here, you can see we can change the 3D glasses effect there. So that it's used as a toggle during the title screen for our 3D mode, and during the gameplay we can pause the game and then we can press fire 2 to toggle the 3D depth in 3D modes. So that's quite a handy workaround for me there to get an extra button in there. Now here's our interrupt handler. There's a lot of it, unfortunately. We're going to go over it quickly. So the first thing we're doing here is we're checking if we're still going to register the light gun, because if the light gun was pressed recently, we're going to ignore it for a little while. If we are, then we're going to check the light gun fire button here. And what we're doing here is we are reading in the fire button here, and we're seeing if the fire is pressed, and if it's not, we're just going to skip over the whole next bit. If the fire button is pressed, then we are going to basically set our entire palette to white. We're then going to read in our scan line counter and check if we've now got to the bottom of the screen, because if we have, then the player must have missed. If we've not got to the bottom of the screen yet, we're checking the light sensor and seeing if the gun can see brightness. And when it can, then what we're going to do is we're going to read in. We read in from 7E to get the vertical position. We read in from 7F to get the horizontal position, and this will be set as soon as that light gun detected light. So we've now got the X and Y position. We're then setting the fire down to flag, which is usually the second fire button, but if we fired off screen, this will be our reload. And we're then just converting our X and Y coordinates to the game coordinates for the hit detection. We're setting the fire flag to register that a bullet was shot, and that will later on decrease the amount of bullets the player has and things like that. We're then setting a timeout so we don't check the light gun for too much time. Now, the auto fire, the game does have a fully automatic mode, and that does require relatively fast reading of the light gun to get to the new position for the machine gun effect. Now, if fire isn't pressed, then what we're doing next is we are toggling the shutter glasses. We are alternating the eye here, and then we are branching to the left or right eye code as required, and this will set up the correct eye. We'll have a look at that in just a moment. Final thing we're doing at the end of the interrupt handler is we are doing our music. Now, the music uses a modified version of Arcus Tracker. It's my simplified version that runs from ROM, Arcus Tracker 1 that is. So we're playing the music here, we're using that, and we're using AY emulation because Arcus is an AY system, but I've got a simple sound emulator that allows me to use it on the Master System. And then what we're doing here is we're clearing the interrupt, because if we don't read in from the VDP control port, the interrupt will keep firing forever, and that will make our game run very, very fast, which will be quite bad. So that's what we're doing there. Here's our code for the right eye, or the code for the left eye. The only difference is we're using a different cache and a different set of palette data. Potentially the palette data will be different in the 3D glasses, the colored 3D glasses. In shutter glasses mode, they're both grey palettes, so it will just depend. Now, we've got a cache in RAM. We're basically transferring this entire cache to VRAM every time the frame updates. Now, we could have in theory used the two different tile maps. The Master System can have a tile map, I think it's 3800 or 3000. However, for this game I was using too many tiles. The pattern data and the tile map data will start to overlap, so using two tile maps would have meant less data for the patterns, and that wouldn't have left enough data for the patterns. So I'm just using one, and I'm doing it all in software. So here we're setting the correct palette, and then we're transferring the palette to VRAM there. That it's just 4 colors we're transferring there because it's a 4-color palette. Then what we're doing here is we're setting the memory address to 7800, which is effectively writing to 3800. The bit 6 needs to be set to 1 to denote a write there. And then what we're doing here is we're effectively copying hexadecimal 600 bytes to VRAM, and that is the entire tile map. So we're effectively transferring the whole tile map to VRAM there. And then once we've done that, we're just returning and finishing our interrupt handler, updating the music. So that's our interrupt handlers, but what about the job of transferring the pattern data to VRAM? Now, unfortunately, because of the limited memory, we're actually having to have 2 different sets of data, or 3 even, one for the title screen, one for the introduction you can see here, and one for the gameplay. And unfortunately, the title screen doesn't have any font, so we can't show the high score like the other systems because there weren't enough tiles left. It was a real struggle to get the 2 versions of the tile map, because of course this tile map is 3D, so there's 2 different versions of it. So the Master System screen you can see there would take 768 patterns to cover every tile of the screen uniquely. However, I think there's only 480 we can actually use before we run out over memory. Theoretically it's 512, but in practice it's 480. And I needed to have two different versions for the 3D effect, and so if you see it in 3D mode, you will notice there's some graphical glitches, so some pixels are missing and some things are kind of a bit messed up, and that's because I've had to replace tiles with things that are nearly what I wanted to reduce the number of total tiles down to an acceptable number. Anyway, when it comes to transferring the data to the screen, well, we've got two things we have to do. The first is pretty straightforward. Basically, we take our bitmap data and we transfer that to VRAM. And then the second thing is, during our sprite drawing, we actually need to use the miniature tile maps as the source for the tiles we need to show to the screen. We're going to have a look at both of those now. So we've got this function define sprites A here. Now this takes source bitmap data, which is just raw 4-color data, not 16-color. We're going to convert it. We've got a destination address here. This is destination 0, so we're writing to the start of VRAM. And then H and L here are a bit weird. They actually multiply together and they're the grand total. This was modified from some other code, so it's a little bit odd maybe, but that's the way this works. So first we're transferring our bitmap data to memory address 0, and then we're transferring our font data immediately after the bitmap data, so that's 333 times 32, and that's because that's how many tiles we are defining in our bitmap data here. And the font actually also includes the cursors. The cursors are included in that font data. Now the transfer routine is pretty straightforward actually. All we're doing is we are selecting the memory address we want to write to, and then what we're doing is we're transferring 8 lines of each tile. The first 2 are read in from our bitmap data. The second 2 are 0, and that's because our source data is 4-color on all systems. Here is our source data here. It's only 4 colors, not 16 colors. So that's why we're setting those second 2-bit planes to 0 there, and just effectively blanking them out. And then we're repeating until we've transferred all of our sprite data. There is an alternate version which I'm not going to go over really here. This is a double height version. The title screen graphics are not 8x8 tiles, they're 8x4 and they're doubled up. So that's an alternate version that handles that doubling up. Now when it comes to drawing a character to the screen, we've got our show sprite here. Show sprite R and show sprite L do the left and right eyes, but all they do is effectively write to a different cache. So they're basically the same routine. Now what we're doing here is we're going to load in from the information that defines each of these sprites. Now the information, if I go to the default information, is this sprite info here, and this is in the same format for all of my systems. Basically the first word is a pointer to the sprite information, sprite data, and then there's an X and a Y in pixels, and we'll need to convert that in this case to tiles. It's better to have something constant on all systems, I believe, so that's why we're using pixels, not bytes or tiles, because that would be different on every system. Now usually this would point to the bitmap data, but on this system there's a bit of a uniqueness. It points to a miniature tile map of the tile numbers, and you can see here these are tile numbers. So 1 is tile 1, 2 is tile 2. Sounds fairly straightforward, but well, what happens when we get over tile 255? Well, when we've got a 255, that's a 2-byte tile. So here you can see 255 followed by 4, and the tile number there is 255 plus 4. So it's a flexible format that's 1 or 2 bytes, usually 1 byte. So that's what we're working with. So here we're loading the address of the tile map, and here we're loading the width and the height that we're going to show. We're then converting that from pixels to tiles here, and then what we're going to do is we're going to show the sprite to the screen. Now the first thing we've got to do here is we've got to check if the width has been changed to 0, because this routine is run after a set of cropping has been performed. So if we've cropped our sprite down to nothing, we're not going to want to show it. So what we're doing here is we're loading in our X and Y position that we're going to show the sprite to, and then here we're loading the amount that we're going to want to crop off the side of the sprite. So if our sprite is partially off the screen, we might need to crop part of it off. So this is to handle the cropping, because we're going to have our game screen like that, but our sprite might be partially off the screen like this, in which case we're going to need to crop that part of the sprite off the graphic, and that's what this code does here. So basically what we're doing here is we're adding the X offset to the start of our tile data, and that's going to be the amount we need to remove from the side of the tile map, because of course we're working in tile maps here, so we might be removing one or two of these tiles, not sprites here. Now what we're doing next is we're calculating the ending positions for our loop counters, and then we're actually going to start to do the drawing routine. Now there is another problem. This game engine was designed to work with systems that used XOR. This system doesn't use XOR. Now there was basically two possible ways I could do with that. Rewrite the entire multi-platform code to work in a completely different way, or do a nasty bodge, and I did a nasty bodge. So basically we've got this do remove sprite function. If that's set to 1, rather than drawing the sprite to the screen, we're going to draw the tiles to 0, so blanking the sprite out. Now this isn't as good as XOR, because XOR, if two things overlap and then you draw the one sprite again, the other will be left. This won't do that, but it was the best I could do under the circumstances. So that's what we've got basically. That's all we can do in this case. So we're calculating the memory address within the cache that we need to write to, and then we're reading tile numbers from the source tile map, and then we're setting IX to that tile number. But then we need to check if we're over 255, because if we are, we need to add effectively another byte, and we need to add that to IX. But once we get to here, we've got the correct tile number. And then what we're doing here is we're setting the tile in the tile cache to the correct tile number, and of course that will be transferred to the VRAM during the next interrupt. We're then repeating until we've done the end of our line. Once we've done the end of the line, we need to remove any cropping off the other side of the sprite, because of course you saw before, well, if the sprite's over on the left hand side, we need to crop at the start. But if the sprite is on the right hand side, or even on the left hand side in fact, we will need to then remove either this part to get to the next line, or after the first line this part to get to the next line there. So we do need to crop in both cases there, and that's what we're doing here. So we're reading in a tile here, and we're basically moving along one, but then we've got to check and see if it's 255, and if it is, we've got to skip another tile. So that's what we're doing there. Now once we've done our line, we're then basically incrementing our Y counter here and seeing if we've got to the end of the tile map, the miniature tile map, or the sprite if you will. And we repeat until we have, and then when we have, we're just resetting the sprite clip to 0 for the next iteration. So that's how we are setting that miniature tile map onto the screen, and that's all we're going to be covering today. So you can go to my website, you can download the source code to Suck Hunt, you can download the built game as well. As I always say, you're welcome to use the game code in any way. If you want to take fragments out of it and make it into your own game to whatever extent you find useful, you're welcome to do so. Even if you somehow manage to do that commercially, I don't believe you can, but if you manage to make money off it, good luck to you. If you want to support my content and you want to see me make more games like this or better games in the future, you can do so by buying my book, Learn Multi-Platform Assembly with Chibi Akimas. It covers Z80, 6502, 68,886 and ARM, and it's available from Amazon now if you want to back me. You can also back me on Patreon if you prefer. Anyway, I hope you've enjoyed this. Hopefully you'll subscribe to this channel, because then you'll see the next episode where we're going to look at the more of the source code of Suck Hunt. We're going to look at the introduction animations and also the palette routines, and going to look at how the palette switching works. Anyway, hope you've enjoyed this today. Thanks for watching, and goodbye.